Hello, my name is Dave Benham, and some of you may have seen me play Native American flutes, perhaps with or without synthesizer. Recently, over the last year or so, I've been really enjoying VCV Rack and pairing that with my flutes. And part of that process has been in watching people like Omri Cohen and others do tutorials. And I thought, well, why don't I give my hand at trying to create a semi-educational video. But this is a two-way street, so I want to kind of share some discoveries I made. But at the same time, there's some things that I don't understand, and I could use some help explaining why I'm getting the results that I'm getting. So about a year ago, I was having some fun with no input mixing, where you take something like a Mackie mixer and you just do feedback. You just patch it, have the mixer feedback into itself, and you can get all kinds of squelches and squeals and all these dynamic sounds that you can get out of it. A lot of fun. I'll post a video. I'll post a link to a video that I made with that. And I thought, okay, what could we do to use a mixer to create some oscillations in VCV Rack? And I succeeded, and I'll show you how I did that. But I was expecting wicked, really nasty aliasing, and to my surprise, I'm not seeing that aliasing, or not obvious aliasing, and I'll get back to that. So in order to get there, let's demonstrate how I created an oscillator out of some mixers. So I'm going to start with knobs. I'm going to use that as my mixer. I love volt knobs. I use it in almost every one of my patches. And to kind of monitor what's going on, I'll get the NIST voltmeter. And here we go. Put that up there. So, all right, this is going to be boring, right? We've got unipolar voltage here, 0 to 10. And let's put this down to 0, and let's put some feedback on here. So put that up to attenuation up to 100%. Feed it back into itself. Let's turn this voltage up, and boom, just very rapidly, it just starts counting up. And if I let this go, it's going to go to infinity. But if I could come up with a way of either interrupting the voltage and then have it start again, it could, you could get a sawtooth wave. Or if I could come up with some way to, as it's counting up, once it reaches a voltage, have it start counting in reverse until it gets to a -5, and then counting forward again, we can get a triangle wave. So the saw wave is simpler concept to think about, but the triangle wave, I think, is easier to build a good, stable triangle oscillator out of a mixer. So I'll start with that. In order to do it, I need a comparator and a switch. So I'll use Bogue Audio comparator, and let's also get the switch. And I think there we go. Okay. So to do this, I'm going to use both the top and the bottom knob. I'm going to use the mixing is going to be happening in the knob 2, and the knob 1 is going to be providing the incremental voltage that gets fed into the feedback loop. So here we got a comparator. It's got an A input and a B input. Right now the default's 0, no inputs, and everything's at 0. We've got, you can either compare A against B, or you can A greater than B or A less than B, or you can do, are they equal? And when you're doing equal, you have an option of having a window, and by default the window's set to 5. So if A is within 5 volts of B, then it's considered equal by default, and once it exceeds that range, and then it becomes unequal, which is perfect because we want to go between -5 and 5 volts, so 0 volts right in the center. So as long as it's in that range, it's going to be either counting up, it's going to be counting in one direction. As soon as it gets outside that range, we want to fire a switch, which will somehow reverse the voltage until it goes back down the other way, and you can oscillate back and forth. So we want to set this lag to 0, and we're going to be we want to set this bottom knob to bipolar. It's at 0, so there's no voltage to start out with. And we'll put that into our comparator, and we'll put it into our voltmeter so we can verify it's at 0. And then if it is not equal to 0 within 5 volt range, then we want to send a trigger, or send a gate to our switch, and we want to put it in latch mode so that it reverses direction. And the direction is going to be coming from our upper knob. It's going to be providing the incremental voltage, and to make it so we can have finer control over and not have it go really quickly, let's attenuate the signal that we feed into our feedback loop. We'll set it at we need 2 signals. We want to be able to go up or down, so we need minus 0.05 or plus 0.05. So minus 0.05, and this other one I'll set to plus 0.05. We want it to be symmetric, so we have a nice even triangle wave. So we take the output from this knob here, send one of them to the high, and send the other one to the low. So, and they're both coming from the same gate, so one or the other is going to be active. So we'll take this one output and send that to the negative, and take the other output and set it to the positive. And if we push this up, we don't have the feedback. I'm sorry. We need to get the feedback from the output of knob 2 back to itself at 100%. Now, if we add a little bit of voltage, you can see that it's oscillating back and forth. And if we put min-max mode, you can see that it's going between minus 5 and 5 volts, perfectly, exactly what we want. And of course, it overshoots a little bit, right? Because it has to exceed the 5 volts, and depending on how the amount that we're adding, it as we go up, it's going to exceed it by more and more. But still, it's generally within minus 5 to 5. And we can go ahead and listen to this. We'll go ahead and take this output from here, and we'll, in fact, rather than, well, I'll feed it back into my input here, and turn that up. Ooh, low note, and we can change the frequency. The greater the step, the higher the frequency. And then we can also look at it on the scope. There's our triangle wave, and even that. Let's bring in the Bogue Audio analyzer for frequency. We can look at the frequency profile. So we'll take this and put that in there as well. And we want this to be ultra. Really be able to look at that. And there's what we expect for a triangle wave. All the odd harmonics going down. But as I go up, right, I don't see any aliasing. I would expect there's some reflections to be back and see some other frequencies that we wouldn't want. And the other thing that's kind of interesting, let me turn this down just a little bit again. It's not a continuous change in frequency, it steps. So that's kind of interesting what's going on here. I'll come back to that later, but let's go ahead and move on to the saw wave. But actually, before that, let me put a mutes in there so we can turn things on and off really quickly. I'll put a mutes. We'll take the output from our oscillator, take that into here, and we'll also feed it into our scope, and I will feed it into our analyzer. So if we turn that on, we got it all going again. Okay, we can turn that off. Now let's work on a saw wave. So we'll get another knobs. And it's pretty easy to generate a saw wave, but it's not, but in an unstable way. So I'll first start with that. So again, we're going to need a comparator, and then rather than a switch, because we're going to grow and grow and grow until we reach 10 volts, and then we want to shut off all the voltage so it falls back down to 0. So we'll use a VCA. And I tried the Bogue Audio VCA, and it didn't work very well. I don't know if it's nonlinear response or if there was a timing issue. I'm not sure what was going on, but I'm going to stick with just the VCV VCA. And we're going to need 2. So I'll go ahead and use VCA 2. So if we, it's already bipolar, it's at 0, so we can put our feedback in. Let's go back to green here. We can get our feedback in, and then we only need positive voltage. We don't need the negative, but we're already at 0.05. So if we send the output of our knob oscillator into the A again, but now we want to set the B to 10 volts. And as long as the voltage, the output of knob 2 is less than or equal to, is less than 10 volts, then I want to continue to increase the voltage. So I can take A less than B. That'll be a 10 volt output, and I can pass that into the first VCA, and I'll pass it into the second VCA as well. And so I want to take the output from my incrementer into the first VCA, and put that attenuated at 0.05, and I got rid of the feedback because I forgot I need the feedback has to go through a VCA. So I take the output of the knob 2 into the second VCA and put that back in as feedback, and we can look at the output of this, and it's 0. All right, so let's see what happens when I pump this up, and yep, it's oscillating back and forth between 0 and 10 volts. We actually want a bipolar signal, so let's put an offset in there. So get the Bogue Audio offset, put the signal in, set the offset to -5, and put that in here. And now we can see it's going from -5 to 5. We can look at the output on the scope. I'm going to go ahead and create a second scope. You'll see why in a bit. And let's put this audio signal that we're getting out of our oscillator and through another mutes. Put that into our second. And why is it so low? Let's see. Here we go. Right. So there we got a classic saw wave. what we expect. We can listen. We can put that into our analyzer as well. We can see that nice frequency spectrum there, and we can listen to it. Let's bring that's down. That's good. Let's go ahead and put that in. And here we got a saw wave, and we can change the frequency. Just like kind of you'd expect. Here again, there is no visible, obvious aliasing here. Before I go on, what happens if I start playing with this a lot? Oh, what happened? All of a sudden, it just kind of, the signal goes. And what's happening is, if this were a instantaneous circuit, right? We've got this switch effectively. The comparator is detecting it when it exceeds 10 volts, and then it shuts off the voltages and to go back down to zero. The problem is it's not instantaneous. There's multiple sample delays in there, so it goes down to zero for one sample, but in the meantime there's some residual voltage elsewhere in the circuit, and the switch turns back on, and then it just messes up the whole signal. So what we need to do is we need to put a delay of some kind, so that when it turns off long enough to make sure that all the voltage is cleared before it turns back on again. And the way I'm going to do that is with a D gate to turn. I'm going to treat the comparator as sending off a trigger, and then I'm going to turn that into a gate of X number of sample lengths. And I'm going to need two things for that. I'll keep this. I'm going to need first a D gate from Bogue Audio, and I'm also going to need a NOT gate I'm going to use the one from Submarine. So now the logic needs to be kind of reversed a little bit. Instead of checking to see if A is less than B, I'm actually going to check to see if when it exceeds 10 volts, I wanted to send a trigger to my gate generator that'll then generate a signal of a positive signal for 5 samples, and I'll explain why it's 5 samples in a minute. And then I want to take the inverse of that, so that most of the time it's counting up, and then when it hits 10 volts, it's going to turn off. Through the negation, it's going to turn off the signal, so it'll turn off our VCA. And it'll turn it off for 5 samples, and that'll be enough for all the residual voltage to clear out from our whole circuit. So we can we've got the same output from the knobs going into our comparator. Now we want to, if it's greater than or equal to B, greater than or equal to 10 volts, we want to take that and send it to our trigger on our delay. And the delay that we want is 5 samples. And so if my engine's running at 48K, I did the math, and it ends up being 0.0001017 seconds. So I'll just type that in here, 0.0001017. And I'll take that gate, put that into a NOT gate so I can negate it, and then take that and use that as my to drive the VCA. And now we've got our same triangle. I'm sorry, we've got our same saw wave, but now I can play with this at will, and it never gets out of sync. It never kind of goes to hell. It always works. So a nice low. So why did I pick 5 sample cycles? So if we just count the number of cable connections we have to do to trace it through the circuit here. If we start from our oscillator, we go into our comparator, that's 1, and then into the D gate 2, into the inverter NOT gate 3, and then going into the VCA 4, and then from the VCA back to the mixer for the feedback loop. That's 5 samples, 5 sample delay. So that's the amount of time that needs to be. All 5 samples have to be accounted for to let the voltage go down to 0, so that all those voltages that are in the circuit throughout those 5 samples can be cleared through, and that works out pretty well. Let's look at this a little bit more. We can have the triangle, we got our triangle and our saw wave, we can actually sync them up. If I just turn this down to 0 and then take the output of my controller up here at 100% to control this, now it's going to, this one knob is going to control both oscillators. So if we turn this on, they're in sync, they're at the same frequency. They can get out of sync, so there's some interesting stuff going on there. They kind of go back and forth between a little bit off, and then they lock in again. But anyway, we're controlling both oscillators with the same knob, and we can see the frequency spectrum of both of them. So let's just turn off the triangle and focus on the saw wave. No apparent aliasing, but this slope here is not quite as much as I would expect. And if I put this up, it's pretty flat. It's not going down anymore, and that could be a clue, right? Let's put this at linear. It makes it a little easier to see what's going on. Where's the aliasing? Well, to investigate that a little bit more, I will actually bring in a normal an LFO. So I could use a VCO, but that's got anti-aliasing. I want to use an LFO that doesn't have anti-aliasing, so we can investigate this a little bit. What does a LFO look like? So let's, I'll use 4FO, and the reason I want to use that is, besides the fact that I'm focusing on Bogue audio, it's got phase control, so I can bring the waveforms in sync with each other in phase. So I'll also need, I want this to follow the frequency of my mixer oscillator. So I'm going to use NIST pitch to voltage. I am amazed how well this works. I can take the output of my triangle wave as input to the pitch to voltage, volt per octave. And then I can use this output as my volt per octave, controlling from my LFO. I need to put this at C4, I think it is, 261.6256 is my 0. I want that to be 0 volts. So 261.6256. And I can take the audio out from here, put that in to another mute, send that to my mixer, also send it to the scope, and send it to the frequency analyzer. And let's turn them both on, and you can see that it follows really nicely. Except I want this to be a triangle wave. There we go. So we've got a triangle, both of them generating triangle waves. They're it's tracking beautifully. I'm amazed at how well it tracks. And if I want, I can adjust the phase of the LFO so that it's in sync with my mixer oscillator. I can make them out of 180 degrees out, and it should just about cancel each other out. And it almost cancels out, but I think it doesn't quite cancel out because I think the voltages aren't 100% the same, right? The my mixer oscillator overshoots a little bit from the 5 and minus 5 volts, so that's why they don't cancel out. But let's bring them back in phase with each other again. Sorry. Back in phase with each other. I can do the same with the saw wave. So, boom, put this down here, and put that in there, and we will take the output from the oscillator here as input into the pitch to voltage. Take the volt per octave into our LFO. It's already set at 261.6256. Set it to a saw wave. Take that output and send that to another mute. Send that to our mixer. Send it to the scope, and also send it to the frequency analyzer. And now we'll turn on my mixer oscillator, and then we'll turn on the LFO, and there they are. They're following each other as well. And just like with the triangle wave, I can change the phase of, whoops. If I go to the right LFO, I can change the phase to line them up. So now that we have a regular LFO, remember that as I change this, it's stepping. It's not a continuous frequency change. But with the LFO, I can detune it, and it really is continuous. And now here we see our aliasing. So and that's the clue here as to why are we not seeing it before. If we let's zoom into the high end so we can see what's going on a little bit, and we'll set this back to 261.6256. So here we've got our frequency. It's linear, and it's hitting. There's a peak right at the Nyquist frequency, so that the next peak would be right about here. It reflects back, and it ends up reflecting right back on a natural harmonic, on one of the harmonics, and every one of those reflected harmonics that exceed the Nyquist frequency end up reflecting onto one of the other frequencies that are already there. So there's no visual or nothing that we can hear as far as aliasing. But the moment that we start to detune it, bam, we can see all these all this aliasing come into play very quickly. So that's mostly what I wanted to show. What my question is, why when I create an oscillator out of a mixer like this, why is it constraining the frequency to integral multiples or divisions of the Nyquist frequency? It doesn't make sense, because as far as I know, right, the knobs is using, it's double floating point precision, I should think, and it's not infinite, but virtually infinite gradation of variability of the incremental step. So the slope of the saw wave or triangle, whichever we're talking about, should be able to hit all the various values. But for some reason, it's not a continuous variation in the slope. It's just jumping into integral divisions of the Nyquist frequency. So hope you all found this somewhat interesting, and I hope someone with digital signal processing experience can shed some light as to what's going on here. I'd be really curious. Hopefully you can do it without a lot of math. I can follow along math, but it's not fun. If you can just kind of whether graph or something, I don't know, give an explanation as to what's going on. You can either post it, if it's simple enough, you can post it as a comment to this video, or I'll put a link to a VCV community post. It might make more sense to put the explanation there. So I hope someone can shed some light, and hope this was instructive to someone out there. So thanks for your time, and I'll talk to you later.